this. Let us see the EMF equation of a transformer. And first, let me take the transformer generalized structure as we seen previously. So, like the transformer are of two category. One is core type, another is shell type. So, I am taking core type transformer here. So, this is the core of the transformer, for which I am putting two coils for this, as like this. This is the coil which is connected to power supply side, means input side. So, input side coil is usually called as a primary coil. I will write as PY, means primary coil, where it is connected to the source input. So, input we are giving here. This is what the input. Once we give the input may be voltage source or current source, which we are applying between 1 terminals. As a result of that, what happens? There will be current flowing through this conductor. That current which is passing through this coil will try to establish the flux, and that flux lines will be confined to the core, and which is passing through this core in this way. And if we place one more coil on the other side of this transformer core, then this whole flux is going to be linked with this. So if this is 2 dash, now you should observe that the interesting thing is that, so the rate of change of the flux lines, that is d phi by dt. Once we know rate of change of the flux produced by this primary coil, then I can say the induced EMF inside this coil number 1 will be that rate of change of flux into number of turns of this coil, primary coil, whose number of turns is N1. Similarly, if the secondary coil number of turns is N2, then this same rate of change of flux into N2 will give the induced EMF inside this coil, which may be some other induced EMF. Let us say this is E1, this is E2. Now our main motto is finding what will be the induced EMF E1 and E2 in the form of various parameters. So for which, so what we will do is that, just let me give you some notation that, so here N1 is the number of turns in primary, and N2 is the number of turns in secondary. This is what the secondary coil, and let us say flux phi m is the maximum flux in the core in Webers. And usually you might see that, so the flux and flux density relationship. So flux phi m is equal to maximum flux density into area. Or you can say flux density is the flux by area. Flux per unit area is referred as flux density, where A is the area of cross section of the core. A is the area of cross section of the core. Dm is the maximum flux density. So now just try to understand in simple manner as like this. For example, if I'll give here some input, so the nature of the input is, let us say, voltage source. So what kind of voltage is? Sinusoidal voltage, which is varying as sinusoidal. If the given voltage or the input is sinusoidal, the corresponding product outcome current is also sinusoidal. If the current is sinusoidal, the corresponding rate of change of flux is also sinusoidal. You had seen in the animated video that if the current is changing, flux also changing in sinusoidal manner. Now we can have some understanding as like this. If I'll take such a sinusoidal flux with respect to time as like this, let us say the flux nature resembles the sinusoidal nature as like this for one cycle. This is for one cycle. These kind of things may repeat again and again. This is for one time period t. Now try to observe this is what the flux phi of t, which is varying with respect to time. Now try to observe this flux is reaching to the maximum value within 1/4 of the time interval. Let us say this is t by 4 intervals. Next, this is t by 4 interval, half interval up to this half cycle, and remaining half cycle like that. Within 1/4 of the time, the flux is reaching to the maximum value. How much is that maximum flux? Phi m. This is what the maximum flux in the core. Why? Because core flux nature resembles the applied voltage. Applied voltage nature is sinusoidal, so flux also sinusoidal. Clear? Now, just we would like to understand in a generalized way as like this. The average rate of rate of change of flux. The average rate of change of flux. That means for what time interval the flux is changing. See, for 0 to t by 4 interval, the flux has changed from 0 to maximum. Next, t by 4 to again let us say t by 2. The flux has changed from maximum to 0. Then again t by 2 to 3t by 4. Then flux has changed one more time 0 to minus 5m, and from 3t by 4 to t the flux has changed from minus 5m to 0. Means in this way you can observe that at any instant the change in flux is 5m. Like 0 to t by 4 change in flux is 5m, and t by 4 to t by 2 change in flux is 5m, and t by 2 to 3t by 4 change in flux is 5m, like that. So average rate of change of flux, average rate of change of flux, rate, whenever you see this rate, it means that in the denominator you will have time. So this we can say how much is the flux change? 5m. For how much time interval? It is 1/4 time interval. So that is t by 4 intervals. For every t by 4 interval, the flux is changing 5m. That is what the average rate of change of flux. Okay? So now you can observe this. This can be made. So we seen previously the time is reciprocal of the frequency, or frequency is reciprocal of the time period. So I can write this as, so like 5m, that is 4 5m by t, where t can be written as 1 by f, or 1 by t can be written as f. So I will get this as 4f into 5m. 4f into 5m. This is what? This is the average EMF. This is the average EMF, average EMF per turn. Per turn. Why I am saying this as average EMF? Can you tell me? Just you can see this somewhere. I had told you Faraday's laws of electromagnetic induction principle. See that the rate of change of the flux is indirectly equivalent to the EMF. Now can I say the rate of change of the flux d phi by dt is what? The EMF E divided by N. It may be negative. It doesn't matter. That means EMF per turn is what the rate of change of the flux. Clear? So rate of change of flux the average rate of change of flux is what the average EMF per turn, which is equal to 4F phi m. 4F phi m. Now we know that this phi is phi m or phi the flux phi is sinusoidally varying is sinusoidally is sinusoidally sinusoidally varying varying. And for sinusoidal natures, we already discussed some important points while discussing about the RMS value and average value. So what is that is form factor. What is the form factor? So RMS value to average value ratio, AVG value, that is average value ratio, is referred as form factor. And for a sinusoidal, how much we got the form factor? Do you remember that? So RMS value we will get usually Vm by root 2 and average value 2 Vm by pi. As a result of this, we got 1.11. If you could recap, it will be 1.11 for any sinusoidal waveform. Now, from this basic understanding that flux is varying sinusoidally, so I can write RMS value of EMF per turn is equal to, from this can I write RMS value is equal to average value into 1.11. So that is 1.11 into, I'll say that directly this entire thing. Average EMF per turn. Now which is equal to 1.11 into 4 into F into pi. This is what 4.44 F phi m. And we know that phi m can be written in terms of the flux density and area. So if you want, you can express this in terms of as like this 4.44 F phi m can be written as B into Bm into A. Flux phi m can be written as Bm into A. So this is what the induced EMF per turn. Induced EMF per turn. So this is a generalized expression. Now, in transformer perspective, we know that induced EMF per turn in this coil and in this coil both are same. Why? Because see that same amount of the rate of change of flux d phi by dt is associated with the coil 1 and coil 2. So I can say the amount of the induced EMF in coil 1 is equal to the rate of change of the flux into number of turns of the coil 1. So that means I can write this one as like this. Now the induced EMF, which is of course RMS value. Okay, I am talking about RMS value quantity. RMS value of quantity. RMS value. What induced EMF? RMS value induced EMF. Where? In primary winding. Let me write in short form, primary coil is equal to, can I write in this way? RMS value of EMF per turn into coil 1, that is primary coil, number of turns. So per turn into turns will get cancelled, EMF will be left out. So EMF equation for the primary coil, usually RMS values are represented by capital letters, so I am writing capital E1 is equal to 4.44 F N1 phi m or 4.44 F N1 Bm into A. These expressions I am writing in the same way, I am importing over here just by multiplying N1. Similarly, just you can think of that for the secondary coil. So tell me, What about for secondary coil? Say induced EMF in secondary coil. So here and here and here, and this become E2. So these changes going to take place. The secondary coil, SEC secondary coil, is the RMS value of EMF per turn into number of turns in the secondary coil, N2. So induced EMF E2 is equal to 4.44 F N2 phi m or 4.44 F N2 Bm into A, whichever quantity will be given. And from this we can simply take that the ratio of these induced EMF as E1 by E2, which gives as, so all quantities are same, so which gives as N1 by N2. So in continuation to this, we will see in the next class. This is what the transformation ratio. Okay. Thank you.